Pharmacogenetics specifically is looking at how gene variants affect prescribing. So when we prescribe, we think which medication, which dose. Pre-prescribing, as clinicians, we think are more conservative measures appropriate. So it's funny, there are a lot of research scientists who, through no fault of their own, have zero or very little clinical experience. As clinicians, we realise less conservative measures first, including expectant management, which is known as the waiting time to see a psychiatrist. So, so sometimes people will spontaneously remit while they're waiting to see you, situational stresses, they get supports, and then you graduate to prescribing. So I think another way of critiquing studies is they really aren't looking at the people who have failed conservative steps before, and then in the cohort they study, they'll get a lot of spontaneous remitters, people whose adjustment disorder settles. And so again, you can use your clinical experience, which you've got a lot of, to critique what kind of people have they studied, what intervention did they do, does it make clinical sense? If not, I'd encourage you to toss the paper and just focus on the ones where it was, hey, yeah, this makes sense as a clinical problem. I think they vetted it pretty well. Okay, let's see what they came up with. The term has been changed a lot. Precision medicine will take over because that's how Barack Obama referred to it at the start of the year. Personalised medicine is the other one. He set up a $250 million fund to accelerate precision medicine research, mainly focusing on oncology, but we're trying to also make them aware of the burden of disease. So a lot of the focus has been on mortality. But if you're 99, maybe that's what's meant to happen. Do we want a 99-year-old to live to 120 with cancer turned into chronic disease? People have feelings one way or the other. Do we want the 45-year-old truck driver to not suicide, keep paying tax for another 22 years? So these are social debates. You see how the social dimension comes in, the networking effect. So all it is pharmacogenetics is impact of genes on prescribing, which med, which dose, whether a med is likely to help. That's all you have to do. So the companies that are already offering these services, and there are a few already, there'll be tenfold more, I estimate, in the next 5 years, and they'll all be coming at you. And you will have never seen anything like it in your career, I'm estimating. What they do is, what you do first is talk to the patient, use your clinical reasoning, critique the evidence for yourself, make your own decision, refer to guidelines. They'll take a long time. They'll usually follow the evidence by some years. And then all you have to do if you're in a research trial or a patient getting this direct-to-consumer genetic testing is the buccal brush, which you can do yourself on the inside of the cheek, or a little spit thing. It's got preservatives in it that prevent degradation of the DNA, and then that gets sent off to the lab. In the lab, they shove it into this sort of machine. This is like an out-of-date machine. It's like a 1 megapixel camera. It's really out of date. But they just shove it into a little thing, hit a button. Just like a swimming pool, they fill the reagents, the chlorine, the acid, whatever the swimming pool agents are for this, and it whizzes out answers through a computer. And there are two main types of gene chip that are used. So one gene chip is a whole genome gene chip. It's a misnomer. They just look at 500,000 haplotype chunks. So the human genome can be broken into 500,000 chunks, haplotypes, those chunks. And that's what they do certain studies with called whole genome studies. It's a misnomer. It's low resolution whole genome studies, not stratified for methylation. And if you can say that, you've got some expertise in this area, and you should all be able to say that by the end of the week, or by at least the end of today maybe. The other type of chip is the chip that's going to penetrate sooner. It's called a DMET, or drug metabolism elimination transport one. So they just look at gene variants that seem to plausibly be connected to pharmacokinetics and dynamics for certain drugs like warfarin, where there are particular pathways in its dynamics. In psychiatry, the dynamics of drugs is unclear by and large, so it's really, my view is it's going to be the kinetics. Others, though, have invested their research careers and their commercialisation plans on dynamics. My view is it's easier to understand the kinetics with psychotropics. So a lot of the studies actually just look at those pharmacokinetic and dynamic factors, and they use that chip. So that's all. That's what happens in the lab. One chip, another chip, bit of spit, stick in the machine. In those haplotypes, as I mentioned, this is a thing called a Manhattan plot. So when they do a whole genome sequence, they break it into those 500,000 haplotype chunks. which you've got tag SNPs, and they see if group A versus group B has a different profile. So somebody with schizophrenia versus not schizophrenia. Because they're looking at 500,000 chunks, they need, the statistical power issues are huge. So they need like a P of 10 to the negative 8 for it to be significant, because they're having a bet both ways. These are non-hypothesis association studies, and so they're really looking for they're looking for regions that might have a big effect. The reality is anything that's got a big effect is going to come through family studies. So if something's got a big penetrant effect genetically, we would have seen it in family studies. They're really looking for clusters of things that could be combined that might then give a signature. So in some ways, that's why they do these studies. It's really looking for new markers, particularly for diagnosis, but also things associated with treatment outcome. So that's what a genome-wide association study is. So you'll see papers that talk about genome-wide association studies. That's all it is. The 500,000 haplotype chunks, group A, group B, do they have a different profile of haplotype chunks? Could that be associated with the condition? We need a P of 10 to the negative 8 because we're looking at 500,000 bets. And we have to account for that. That's what a GWAS is. The pharmacogenetic ones tend to look at candidate gene association studies. So they'll look at specific pharmacokinetic, pharmacodynamic, plausible associated gene variants to do a study. And some of the panels, they'll break it down into phase 1 enzymes in the liver, phase 2 enzymes in the liver, and transporters. Transporters are key at the blood-brain barrier, which is my interest, but it looks like a lot of people are seeing what I was seeing years ago now. And so this is probably going to be a key kinetic thing for a lot of CNS drugs. And that's what the full thing does. So basically, from that little bit of spit, you stick it in the machine, it whizzes and whirs, and that gives you gene profiles on all these medication-related gene variants. So the price point of this is low, and it's going to be really low. Like it'll be less than one shoe very soon, depending on the shoe, probably a cheap shoe. And so it'll be there. The question is, does it improve clinical outcomes or not? Is the methodology to answer that question robust? So the good old-fashioned evidence-based stuff, never forget it, never be bamboozled out of it. What they do is when they do a study like that, they'll have their candidate gene variants, like SNPs, and then they'll look at the chunks that are co-inherited, the haplotypes, but that is actually a probabilistic association. So there's another level of error built in. So when they do a haplotype, it's like, okay, this chunk, there's 85% chance it actually is a chunk. 15% chance, maybe it isn't a chunk. So there's an extra layer of uncertainty. And that's why in papers, you'll see pictures like that. You don't have to know the ins and outs. It's just they're trying to justify their chunks as actual chunks. And they do that probabilistically. That's all that sort of plot shows. And you'll see them in papers. So that's what you'll see in a candidate gene association study. So don't be scared. Read them. Use your clinical mind. Use your good old evidence-based hierarchies to conclude. That used to be the price of that DMET panel, but it's less now. It's like 50. So it's getting cheap. One test per lifetime. So one of the other things in the health economics is it's one test per lifetime. So if it has clinical utility, if it has no utility, it's a waste of $100 or $50. But if it has, then it could have lots of health economic impacts.